Welcome everyone. This is question number 27 of GATE 2024. The question asks about the number of non-isomorphic finite groups with exactly 3 conjugacy classes. So we have to find the number of groups up to isomorphism. Solution: let G be a finite group with exactly 3 conjugacy classes. Three conjugacy classes. So the class equation of G will be cardinality of class of identity element of G E plus cardinality of some other class plus cardinality of another class. Now if cardinality of G is n, then the class equation will be n equal to 1 plus k plus n minus k minus 1, where k is the cardinality of the conjugacy class of A. Now by the property of the conjugacy class, we can say that k must divides n, and similarly n minus k minus 1 divides n. Now I claim that GCD of k and n minus k minus 1 is 1. So combining these two conditions, we can say that k into n minus k minus 1 divides n, and this implies k into n minus k minus 1 is less equal to n. This implies n into k minus 1 less equal to k square plus 1. I'll use the condition that k divides n. K divides n, so n must be equal to k into t for some integer t. Observing this equation, we can easily say that k must be greater equal to 2. So n equal to kt is greater equal to 2k. So we can put here 2k into k minus 1 is less equal to n into k minus 1, which is less equal to k square plus 1. So we have 2k square minus k less equal to k square plus k, from which we get k square less equal to 3k. Since k is a non-zero and positive integer, we can say that k is less equal to 3. So here is the bound for k. The possible values of k are 1, 2 and 3. If k equal to 1, then the class equation will be n equal to 1 plus n minus 2, and n minus 2 divides n, which implies n must be equal to 3 or 4. If n equal to 3, that is cardinality of G is 3, then G is isomorphic to Z3, because there is only one group of order 3 up to isomorphism, which is Z3. In this case, the class equation of G will be 3 equal to 1 plus 1 plus 1. So G has 3 conjugacy class. Now if n equal to 4, then G must be isomorphic to K4 or Z4, because up to isomorphism there are 2 groups of order 4. If G is isomorphic to K4, then class equation will be 1 plus 1 plus 1 plus 1, and if G is isomorphic to Z4, then the class equation will also be 1 plus 1 plus 1 plus 1. In either case, G has 4 conjugacy class, so G cannot be isomorphic to K4 or Z4. So in this case, G is isomorphic to Z4. Now second condition, if K is equal to 2, then the class equation will be n equal to 1 plus 2 plus n minus 3. Now n minus 3 mass divides n, which implies n is either 4 or 6. N equal to 4 is not possible because we have already seen this case. So n must be equal to 6, and then G is isomorphic to S3 or Z6. If G is isomorphic to S3, then the class equation will be 6 equal to 1 plus 2 plus 3. If G is isomorphic to Z6, then the class equation will be 6 equal to 1 plus 1 plus 1 plus 1 plus 1 and plus 1. So clearly, if G is isomorphic to Z6, then G has 6 conjugacy class, which is again not possible. So in this case, G is isomorphic to S3. If K is greater or equal to 3, then we can find an upper bound for n using this equation. So this equation says that n into k minus 1 is less equal to k square plus k. So n into k minus 1 is less equal to k square plus k. Now k is always less equal to 3 by this condition. So n into k minus 1 must be less equal to 9 plus 3, which is 12. Now this implies n into 2 is less equal to n into k minus 1, which is less equal to 12, and therefore n is less equal to 6. We have already seen what will happen when n is 3, 4 or 6. So the case left are n equal to 1, 2 and 5. N equal to 1, this is not possible because this group cannot have 3 conjugacy class. Now case n equal to 2, this is also not possible because this cannot have 3 conjugacy classes. So we have to go for the case n equal to 5. For n equal to 5, G must be isomorphic to Z5 because up to isomorphism there exists only one group of order 5, and the class equation of Z5 is 5 equal to 1 plus 1 plus 1 plus 1 and plus 1. So G does not have 3 conjugacy classes. Therefore G is either isomorphic to Z3 or G is isomorphic to S3, and Z3 is not isomorphic to S3. So the number of non-isomorphic finite groups with exactly 3 conjugacy classes will be